Hello, our project is MPI with non-ideal selection fields. I am Sayit Sarper Aslan, and my project group mates are Boran Kılıç and Mehmet Emre Uncu. Here are the table of contents. Starting with introduction, magnetic particle imaging is an imaging modality that uses superparamagnetic iron oxide nanoparticles as tracers. MPI utilizes the SPIOs Langevin response to a magnetic field as an imaging modality, and this response is most pronounced around zero magnetic field, where this point is also described as field-free point, FFP. Using X-spaces reconstruction, our project aims to implement a non-ideal selection field and explain how responses of SPIOs change according to non-idealities such as shifts and warping conditions. Moving to methodology, the general MPI imaging for a signal acquired can simply be described by the equation below, where if we focus on the final form of the equation, which is a convolution of the SPIO distribution with the derivative of the Langevin function evaluated at x equals xst, the FFP. Before we explain what FFP, how we get FFP, we need to explain the ideal selection field, which is described as HS equals GX, and FFP is formed by adding a time-varying magnetic field. In such case, FFP is time-varying magnetic field divided by the selection field. We have chosen two non-idealities for our project, which first of them being shift from a center of the selection field. A shift can be introduced in the selection field with an offset, which in turn creates a similar offset in the FFP as well. For comparison, looking at the comparison with the ideal case and the offset, you can see that it shifts a little bit of positive direction for negative offset and shifts a little bit of negative direction for the positive offset. Moving to inhomogeneous selection fields, we added the inhomogeneous selection field by adding an exponential that decreases from center to the other side, which in response gives a similar FFP as well. Focusing on the FFP, it can be said that point will get compressed towards the center with respect to their actual position XC and YC, where you can see from the compression factor. Looking at the inhomogeneous selection field, you can see that the selection fields are a bit compressed towards inside. For set information for model, we have 12.5 nanometer core radius, image size and FOV is same 60 to 60 millimeters, gradient strength is 3 Tesla, and dry field in the X direction is a sinusoidal that goes from left to right, and dry field in Y direction is a sawtooth with a high frequency so that it can be moved out to the next line before the sweep is finished.
Now I will talk about the dataset. For the simulations, we have generated 3 different phantom images. First, we obtained the point spread function of a single SPIO. For this purpose, we generated a phantom image with a 2 mm by 2 mm point source placed in the FOV. The second phantom that we created contains 25 SPIOs that are 15 mm apart from each other in the field of view. Lastly, we aim to realize our simulation in a more complex scenario that we created a phantom vessel phantom by hand using Microsoft Paint. For the code's main function was inspired from an open source MPI educational simulation GitHub repository. The rest of the code was written by project members, and for the necessary parts of the code, ChatGPT 4.0 was utilized. Now, moving to the evaluation metrics. First, we have the full width half maximum calculations and measurements of the point spread functions of the SPIOs. The equations on the left are used for theoretical calculations of the resolution. The upper one is in the tangential direction, which is the x direction, and the bottom one is the normal direction. It is visible from the equations that the normal direction full width half maximum is larger, and for the simulation results, we measured the full width half maximum value directly from the data by using the basic formula that comes from the definition. And the second evaluation metric was the displacement resolution using the Euclidean distance. This metric is used for the evaluation of the warping effects. It is basically realized by calculating the distance between the centers of the point stress functions of SPIOs between ideal and non-ideal cases.
For results, the first non-ideality is gradient offset. A 2 mm offset was used for both negative x and positive y direction. When compared to the ideal image, it's observed that the resulting image shifts upwards to the left. By increasing the offset amount in both directions, the image on the right was obtained. it's seen that the image shifts more as the offset values increases. The inhomogeneous gradient was used as another non-ideal selection field. Image on the right is obtained with the coefficient k equals 3.5. In the image, the point source are misregistered, resulting in apparent warping. This can be understood from the points in the corners being pushed towards the center. While the points in the center remains constant, the push increases as it approaches to the edge of the field of view. As a result, the corners of the image are rounded. Then the k coefficient was changed to the -10. As seen here, as the coefficient increases, points located further from the center are pushed more. Thus, the image corners are further rounded.
Now I will talk about the point spread function resolution measurements. Here, two different SPIOs has been put onto the field of view, one to the center and the other one 5 mm apart from the left and upper edges. The results for all the cases look identical except for the locations. For the offset case, the shift is visible on the reconstructed images, and for the in the homogeneous case, the location shift gets worse as going to near to the edge. And it is also visible that point spread functions are more spread in the y direction. And this table shows the full width half maximum measurements results. And in the right corner, we have the theoretical results, and the measurements are quite similar to the theoretical ones.
For displacement resolution, error calculations was made between the ideal image and non-ideal image using Euclidean distance. The ideal image was divided into 25 equal squares. The x and y coordinates of the highest value pixel of each square were recorded. Thus, we have 25 x and y pairs obtained. Then, this process was repeated for offset gradient and inhomogeneous gradient. First, Euclidean distance were calculated for three different areas of the ideal and offset gradient. As can be seen in figure, the calculated error values are close to each other, since the offset process is applied equally to all frames of the image. Afterwards, the error calculations were made the same way between the ideal and inhomogeneous gradient for three different areas again. When the results are examined, the error for the green square calculated as 0 mm. This is because inhomogeneity depends on distance and there is no change at the origin. As we move away from the origin, the distortion increases and therefore the error increases.
Here, from the results of the vessel phantom image, the warping effects are clearly visible. Here, the image object is shifted in the offset gradient result, and the compression is clearly visible near the edges in the inhomogeneous field case. For the discussions, this project successfully showed that when the field of view goes beyond the linear region of the selection field, geometric warping artifacts appear in the space reconstructed images, and full width half maximum values of the point spread functions were nearly the same, and the resolution loss was evident in the separability of 2 point sources. And we have some possible solutions to the warping artifact. Those include unwarping process, varying the amplitudes of the focus and derive fields, staying inside the linear region, and calculate the actual field free point trajectory. Those are discussed in the report. These are references. Thank you for listening.
Now we have a quick demo. I'm going to run the code. As you can see, this is the selection fields. The top one ideal, the middle one the offset one, and the bottom one is the inhomogeneous. This is the result of the shifted gradient. As you can see, we have phantom, ideal, and offset images. This is for the inhomogeneous case, and this is for the offsetted Euclidean distance. This for the inhomogeneous Euclidean distance. We have discussed in previous slides. And lastly, we have a phantom of the vessel. As you can see, in ideal image, it's normal compared to the offset one. And in homogeneous image, we have seen the rounded image. The corners are moved toward the center. That's all. Thank you for listening.